Yesterday we took a look at position time graphs, the shapes of those graphs, and mathematically how we determine position, displacement, velocity, and so on of those graphs. Hey, this first graph that's up on the board right now, position versus time, what's our manipulated variable on this graph? What's our manipulated variable on all these graphs? Time. Time is the manipulated variable because it appears on the x-axis. The manipulated or independent variable is always on the x-axis. And, by the way, it always appears last in the title. Now, the first word in the title is position. It's also on the y-axis. That would be our what variable? Our responding variable or our dependent variable. This first graph, what does the shape of that graph mean? What does it represent? The object undergoing the motion described in this graph is doing what? Yeah, it's moving at a constant speed, or specifically because it's position, not distance, we'd say moving at a constant velocity. Okay? The second one, straight line, horizontal straight line, we would say that this one is stopped. Yeah, it's just stopped, not moving. The third one is straight line, but sloping downwards. Yep. Yeah, good. This is a constant negative velocity. It doesn't mean it's going backwards. It just means it's going in the negative direction. If we define towards Calgary as positive, then this is coming the other way, towards Okotoks from Calgary, the negative direction. It doesn't mean that you're walking backwards or that you're in reverse in your car. It just means that your car or you are going in the negative direction, the opposite direction. What's the fourth one mean? Yeah, this one's acceleration, speeding up. Okay. Increasing velocity, you could say. And what about the fifth one, the last one? This is decreasing velocity, yeah, or deceleration, we could say. All right? Now, we also learned how to determine different things on a velocity time graph. I'm going to go actually to the example that we did yesterday. If we want to find the position on a position time graph, then what are we going to do? I'll give you a hint. It's the same as finding the velocity on a velocity time graph, or the momentum on a momentum time graph, or the force on a force versus time graph. What do you want to do if you want to find something that appears on the y-axis of the graph? Up and over. Yeah, up and over. So that's exactly what we're going to do for that. If we want to find the displacement, displacement is just change in position, so we're going to go up and over twice to get two different positions. And then we're going to subtract the two positions. So delta D, the displacement, is equal to position final minus position initial. Just get the two different positions. If we want to find the average velocity, kind of flows, right? Up and over to get position. Up and over, and then subtract the two to get displacement. If you want to find velocity, take the displacement and divide it by the time. What's another thing that you can do, which really boils down to the same thing, but we think of it a little differently, in order to find the average velocity? Displacement over time, or, what's the word I'm looking for? Take the slope of the graph, right? It's exactly the same thing, because if you look at delta D, that is your rise, and delta T is your run. So rise over run, or the slope of the graph, really is delta D over delta T. The instantaneous velocity, as long as we have a nice straight line like this, the instantaneous velocity will be exactly the same as your average velocity. So remember that. Okay, if the average velocity here is, let's say, -5, I don't know what it is, but let's say it's -5, then the instantaneous velocity anywhere along the path will also be -5. Make sense? All right, we have 3 questions for homework, and we're going to take a look at those 3 questions now. Let's start with question number 1. We want to find the position at 7 seconds. How do you find the position on a position time graph? Up and over, yeah, up and over. So at 7 seconds, we're going to go up and over. The position is going to be 30 meters. The displacement between 0 and 5 seconds, well, displacement is going to be up and over, and subtract the 2. At 0 seconds, there's not really much to go up and over. It's 0 meters. But at 5 seconds, we go up and over, and it's 30 meters. So my displacement would be 30 meters. That's my final position, minus 0 meters, my initial position, gives me 30 meters. The average velocity between 0 and 5 seconds, I like to think of this as displacement divided by time. Some of you guys might like to do the slope of the graph. It doesn't really matter. It gives you the same thing. My displacement, I just found in question B, was 30 meters. My time interval between 0 and 5 seconds is 5 seconds. That gives me a velocity of 6.0 meters per second. Somebody asked me yesterday about direction. We're not given a direction here, are we? We have to assume, we have to make this the positive direction, whatever direction that is, north, south, east, west, whatever. It's the positive direction. Well, here's one. What's the average velocity between 0 and 9 seconds? Well, what's the displacement between 0 and 9 seconds? This is my initial position, 0. My final position is 30. So my displacement would be 30 meters. What's my time between 0 and 9 seconds? 9. So 30 divided by 9 is 3.33, I think, isn't it? Why is my average velocity lower in question D than it is in question C? Yeah? Yeah, because we stopped, right? Like, that still counts, but when you stop, that decreases your average velocity. Okay? When I drive, I like road trips, like taking big road trips. When I drive on big road trips especially, I like to kind of, it's kind of a challenge to keep a certain average speed. Like, I like to try to average 100 kilometers an hour, okay, including stops. Okay, and you can do that, right, because the speed limit's usually 110 kilometers per hour, so if you manage your stops, you can average 100 kilometers per hour. But you do have to do that. You have to manage your stops, right? If you're driving for 3 hours and you've driven 300 kilometers, that's great. But if you stop for an hour, clearly your average speed goes down, right? So we have to include the whole time, even those 4 seconds right here that I was stopped for. Okay, my displacement doesn't change. It's still 30 meters, but my time is bigger. Now, what's the instantaneous velocity at 3 seconds? The velocity at 3 seconds. Well, the velocity along here at 3 seconds is going to be the same as the average velocity between 0 and 5, right? So what's it going to be? 6 meters per second. It's the same as this number right here, same as C. What's the instantaneous velocity at 8 seconds? This is a good one. Yeah. 0. Good. It's not 3.3. The instantaneous velocity nowhere is going to be 3.3 because that's not one straight line. That's 2 lines. Okay, the velocity at 8 seconds is 0 meters per second. How come? How come? How do you know it's 0 meters per second right here? Because it's stopped. Yeah, my position isn't changing. It's stopped. So my velocity has to be 0 for that. Second question on that worksheet, the displacement between 0 and 10. Well, my position at 10 is 0. My position at 0 is 14. So I'm going to say my change in position is 0 minus 14, which is negative 14 meters. Does it make sense why it's a negative value? It's a negative value because, like, your position is decreasing, right? So your displacement will be a negative value. The displacement between 10 and 18, well, the final position at 18 is 6. At 10, it's 0. 6 minus 0 is, well, that should be a positive displacement because my position is increasing here. The average velocity between 0 and 10. I'm going to change the color of this, actually. The average velocity between 0 and 10 is going to be displacement divided by time. Or you could say the slope. The displacement is negative 14 divided by 10 is negative 1.4 meters per second. And the average velocity between 10 and 18, we're going to say is, once again, displacement divided by time. This one is going to be 6 meters divided by 8 seconds. 10 and 18 is 8 seconds. That gives me 0.75 meters per second. And finally, the average velocity over the whole thing. Well, the average velocity over the whole thing is, as always, displacement divided by time. What's the displacement over the whole thing? Yep. The displacement over the whole thing is -8. Good. The final position is 6. The initial position is 14. The change in position, or the displacement, is 6 minus 14 divided by my time interval of 18 seconds. We're going to say that's -8 divided by 18, which is the same as -4 divided by 9, which is the same as -0.44 meters per second. And question number 3. Ironically, as we got going, it got easier, right? This is the easiest question that we've had so far. The position at 30 seconds. Up and over. It's going to be 6 meters. The displacement between 0 and 45. Quick, what's the displacement between 0 and 45? How do you know? Because the position isn't changing, right? The line is staying flat. So my final position there is 6 meters. My initial position is 6 meters. If you subtract the two, we get 0 meters. Now, I like you to show work, but in a situation like that, if you just wrote down 0, I can live with that without showing work in a case like that. Okay, some people might need to do the work like that. Some people might just recognize right away that it's 0, and that's fine. The average velocity between 0 and 45, well, this is another one where I could accept you not showing work. The displacement is 0. The time is 45, so the velocity is 0. Some of you are just going to say, well, it's a flat line. Of course it's 0. Okay, that represents an object that's stopped. All right. If you just write down 0 because of that, that's fine. And what's the instantaneous velocity at 15 seconds? Well, the velocity all along there is the same. It's 0. So we're going to just say 0 meters per second there. Good? All right, what do we do if our graph, position time graph, is not a straight line graph? Like in our homework problems that we had there, that we just went over, you saw that they weren't all straight line graph, well, single straight line graphs. We had like a straight line graph sloping downwards and then a straight line graph sloping upwards, but it was two different straight lines. But we do the same basic thing, right? What if we have a curved graph? If we have a curved graph, we can find the average velocity and so on exactly the same way. But the instantaneous velocity, that is the velocity at one moment, of time, we can find that instantaneous velocity by drawing what we call a tangent line. And I'll explain what that means in just a second here. A tangent line at that point, and then calculating its slope. Or calculating the slope is the same thing as saying v is equal to delta d over delta t. Rise over run, delta d over delta t, it's the same thing. So the big thing here is, what's a tangent line and how do we draw a tangent line? Well, a tangent line is a line that we draw with a ruler or a straight edge of some type that goes through only one point and follows the curve at that point. So for instance, if I have a graph that looks like this, and I want to find the velocity at that moment in time, which requires me to draw a tangent line at that spot, then my tangent line will not look like this, because that tangent line goes through a couple different spots on the line. That's not a good tangent line. This is a worse tangent line. Even though it only goes through one spot, it doesn't follow the curve. Right? It intersects it, as opposed to kind of skips off it. I think of, the way that I think of a tangent line? You ever skip rocks in the river? Take flat rocks, skip in the river? Like when you skip a rock off the river, it just glances off of one spot on the water, right? Now, a tangent line is not exactly the same thing because the tangent line doesn't bounce off and change direction. But it does kind of bounce off of the one spot. That's not bouncing off of the one spot. That's like throwing a rock right into the water. Okay, not skipping a rock. So that one doesn't work. Rather, the tangent line that we're going to draw goes through only the one point and follows the curve is going to look more like this. It's hard to draw that without a ruler, but you get the idea. It's following the curve and it's going through only one point. The example that you guys have in the page that I photocopied for you yesterday has this graph. And on this graph, we want to find the instantaneous velocity at 5 seconds. The velocity at this exact moment in time. Now, on the example that I photocopied for you, you can see that I photocopied the graph twice. Do you know why I did that? Because there's a good chance the first time you draw a tangent line, you're going to mess up on it. And sometimes even the second time. But this at least gives you one get out of jail free. Okay, one mess up chance. Now, if you're using a pencil, you got multiple chances to mess up because you can always erase it, right? But even if you're using a pen and you mess up the first time, it doesn't look quite right, that's okay. You got another chance. So what I'd like you to do is to take a ruler or a straight edge of some type. And if you don't have a ruler or a straight edge of some type, then I've got some up here. I'll just ask you to put them back when you're through with them. And draw a tangent line at this spot at 5 seconds. Your tangent line should not look like this, even though that goes through only one spot. It intersects it as opposed to skipping off. That's not a rock skipping off the water, is it? Not at all. It's not going to look like this, although that's better. What's wrong with that one? Yep, Rachel? Yeah, it touches more than one spot. That's not what we want. We want it touching one spot following the curve. So it's going to look like this. No, that goes through more than one spot as well. I mean, realistically, sometimes it might go through a couple, but you want to make it as close as you can to one spot. It's going to look something like this. Does that make sense? Okay, so what I want you to do right now is to take a ruler or a straight edge, and again, the rulers are up there on the desk in the front of the room there. Grab one if you need one. Just put it back when you're finished with it. And on your first graph, preferably with a pencil, draw that tangent line. Don't worry about finding the slope of the line or V equals D over T or anything like that. Right now, just draw the tangent line. All right, so everyone's got their tangent line drawn, and people did a good job, more or less, of drawing their tangent line. I'm going to continue my tangent line here, make it a little longer. Now, remember that you should be using a ruler for your tangent line. Hopefully, you get one that's a little bit better than mine because you're using a ruler. Now, once you have that tangent line drawn, as long as you can draw it, like as stretched out as you can draw it, then what I want you to do is do displacement divided by time, or take the slope of it. So what I'm going to suggest you do there is pick 2 points on that line. Usually those 2 points would be starting point and ending point, 2 points that are far apart. And then let's say displacement divided by time, or rise over run, because really it boils down to the same thing. Here my displacement would be, well, at the end it is 1400 is my position minus 0. Final position minus initial position, 1400 minus 0, over what's my time interval? 15 seconds minus, it's hard to tell what this is. Looks like about 4, 3.5, 4. On a test, if you ever had to do this on a test, the intervals on the graph paper would be much better, so it would be a lot easier to tell where things were. Okay, that's just not a great graph. We're going to say it's about 15 seconds minus 4 seconds. Although yours may be a little different, right? because everybody's line of best fit is not going to be perfect. There is a theoretical exact answer, but this method is not perfect. This method is going to give us a good answer depending upon how good your line of best fit is. So we're going to say 1,400 meters here, or at least I'm going to say that. Yours is going to be a little bit different. I want you to use numbers on your graph, numbers from your graph, not numbers from mine. I'm going to say 1,400 divided by 11 seconds. And what do we get there? 1,400 meters divided by 11 seconds gives me 127 meters per second. You should get on yours, and everybody's going to calculate theirs to see what they do get, a number that's similar to that. It may be a little bit less, maybe a little bit more, and that's okay. I'd give you a range here on a test of acceptable answers. I wouldn't expect it to be perfect. In fact, yours may very well be better than mine because I didn't use a ruler, right? But it should still be somewhere in that range of probably 100 to 150, somewhere in that range. Oh. What I would like you to do now is take a look at the last question, question number 4, on the worksheet that we went over earlier today. It's going to be an instantaneous velocity thing. The back of that example question, first couple questions, position, easy, right? But then you're looking for the average velocity at a certain time. That's when it comes time to draw that tangent line and to do v equals d over t with that. See what you can do with that over the next few minutes now. Sorry, I missed one here. I missed a question here. F, not sure why it's not there. F should be, what is the instantaneous velocity at 4.0 seconds. So do the rest of them and find the instantaneous velocity, which is the one that you're going to draw the tangent line for at 4 seconds.